So in this lecture, we are going to discuss the most of the volume is near the equator. An interesting fact about the unit ball in high dimensional space is that the most of its volume is centered near its equator, no matter in what direction one can choose or define a pole or a north pole. Here, hence the equator is there. So ultimately we need to prove this statement. The statement tells you like this: for c greater than or equal to 1 and d is greater than or equal to 3, at least 1 minus 2 upon c e power c square by 2 fraction of the volume of d-dimensional unit ball has in this. So what we'll consider? We'll consider one unit ball, and in that I think so we'll consider the half unit ball. Because of symmetricity we can do this. So I'm considering the unit ball. This is in d-dimensional unit ball that I'm considering. Okay, but the projection of that one, or we can see in the two-dimensional thing. So the half, that means this much, I'm denoting by h, and that is known as a hemisphere. The hemisphere means half sphere. So if I can prove that most of the volume is centered here in between these two lines, that is, this is the line if I fix. So if I consider this is my x1 axis, this is my x1 axis that I have fixed my pole, then this one is x1 is equal to 0, and this line which we have here, it is, I'm considering x1 is equal to c by square root of d minus 1. So what we have to prove is most of the volume is near or in between these two lines. Due to the symmetricity, whatever will prove for this hemisphere, that is upper half plane, that same things will apply for the lower also. So let me write that here. By symmetricity, we just need to prove that at most a 2 by c e power minus c square by 2 fraction of the volume of the half of the unit ball with x1 greater than or equal to 0 and has x1 greater than or equal to c by square root of d minus 1. So we'll denote this portion that we have here, which are denoted by this green lines, by a. So this portion, that is x is greater than or equal to c by square root of d, will denote it by a. So define or denote a equal to set of all x bar, let's say that is x1 x2 up to xn, belongs to this sphere, whole sphere. Okay, so I'll say that is, let's say the sphere is denoted by s. such that x1 is greater than or equal to c by square root of d minus 1. So it is a set of all points which satisfies this condition. That means all those points which are lies here. And let us denote the H is the hemisphere and H is equal to the upper hemisphere. We will show that the ratio of the volume of A to the volume of H goes to 0. Okay, so this is our objective. What actually we are doing, we are trying to prove that a volume of A divided by volume of H, if this ratio is tending to 0, then we are through, because it will say that the whole this upper hemisphere minus means this much. If it is that goes to 0, then most of these things will be lies in this in between these two lines. That is this pink, yellow line and red line. So that is our objective. So that means what we need to prove, it is actually, if I want to prove that the volume of A upon volume of H is tending to 0, we need to prove that the upper bound of this volume of A. So we note that here that volume of A divided by volume of H, ultimate goal is to prove this is tends to 0. This is less than or equal to what we can write, whatever the upper bound of volume of A, and I want to make this one smaller, so that means it is a lower bound of volume of H, and we'll prove that this quantity is equal to 2 by C e power minus C square by 2. So we shall show that volume of A upon volume of H, as I talked, that is less than or equal to upper bound of volume of A upon lower bound of volume of H is equal to 2 by C e power minus C square by 2. This is our objective. Now to calculate the volume of A is this portion that we have. Okay, so we are taking the integration with respect to x1, because here x1 is changing from this line to this one. So you can just see, observe that we need to have a horizontal line here. So x1 is start from here, sorry, not horizontal, but it is horizontal line like this. So here your x1 is starting from here, C by, and goes to this line is, what will be this line? Since this is a unit sphere, so this plane is actually x is equal to x1 is equal to 1. So the limit of, because I want to calculate the volume of this one. Okay, let me draw that portion here. So ultimate, I need to find out this quantity, the volume of this thing. This is what we have is x1 is equal to c by square root of d minus 1, and this one we have, it is x1 is equal to 1. So volume of A will be the integration from c by square root of d minus 1 to 1. Now we need to calculate what will be this. See, you can, it is not two-dimensional space. If it is two-dimensional space, then we just directly draw the horizontal lines like this, and we can have this in terms of other variables. We can calculate it, because the equation of this one, it is actually x1 square plus x2 square up to xd square equal to 1. That is the equation of this one. But this portion is not this much. That portion is x1 is equal to actually plus or minus square root of 1 minus x1 square, x2 square up to, sorry, x2 square up to xd square. So plus 1 will denote this. But what we will do, we'll take the slice of this much. So this is a slice, and that one thing is a circle. You can just see that it is a, if I have a sphere and if I cut that sphere with the plane, that will represent one sphere, and that sphere, it is actually in one less dimension, because right now we are in d dimension and we have cut that. For example, if you are assuming the sphere in a 3 dimension, and if you cut that sphere with the plane, then you will have a circle, and that circle, it is in 2-dimensional object. So here what we have, in the d dimensional we have the sphere, and we cut by this plane, then it will be a d minus 1 dimensional circle, or I can say in d minus 1 dimension, it is a 1 unit disk. Okay, so what will be the volume of that unit disk? So it is a radius into a face of that d minus 1 dimension. So the radius of this sphere, it is 1 minus x1 square raised to d minus 1 by 2 into the volume of d minus 1 dimensional space, and this integration with respect to x1 that we need to do. So the volume of this A will be calculated in this manner. To get upper bound of this one, we'll use this formula. So what we got here, it is volume of A is equal to C upon square root of d minus 1 to 1 minus x1 square power d minus 1 by 2 v of d minus 1 dx1. V of d minus x1 means it is a volume of that d minus 1 dimensional sphere. Now to get the upper bound of this one, we know what will be the things we have. We know that 1 minus x is less than or equal to e power minus x. This is already we discussed in the previous one of the lecture, that this inequality is true for any positive x. And integrate to infinitive. So, and this integration I am changing from c by square root of to 1, I'm changing to infinity. So if I use this one, we note this and we'll use this one into this expression here. So the volume of A will be less than or equal to, because 1 minus x, instead of x it is x1 square, instead of x it is x1 square we have here. So that is c by d square root of d minus 1 to 1. Instead of that, we can just write down, instead of x we have x1 square, so it is e power x1 square. So that is e power minus x1 square and whole power d minus 1 by 2 v of d minus 1 dx1. This is the things we got using this. We have this. Now what we'll do, we'll still, this is right, volume of A is less than or equal to c by square root of d minus 1 to infinity. See, this limit is till 1, and if I add infinity, so there are many terms I'm adding here. So I'm adding the integration is from 1 to infinity here. Let me write that also. So that is integration from this e power minus d minus 1 by 2 x1 square v of d minus 1 x1 plus I'm adding this term 1 to infinity, e power minus d minus 1 by 2 x square v of d minus 1 dx1. So this is actually gives me c square root of d minus 1 to infinity e power minus d minus 1 by 2 x1 square v of d minus 1 x dx1. Now what we'll do for this one, here I'm adding one more term because I want to integrate this one by integration by parts. Okay, and not integration by part, we'll go, and I want to integrate this quantity, that is e power d minus 1 x1 square. This v of d minus 1 is independent of x1, so I can take that out. But to integrate this one, what we can insert here one more term, that I need x1, because the derivative of this quantity, the numerator, so ultimately what I'm setting is e power fx into f dash of x dx. I want to set this thing. So this is nothing but the v of d minus 1 integration c d minus 1 to infinity e power minus d minus 1 by 2 x square x1 square dx1. So this is the things we have here. So I want to set this thing here, e power fx, instead of fx we have this quantity. So the derivative of this quantity is 2. So it is d minus 1 x1, that is the derivative of this quantity. But that quantity is not bigger than this something. So what we'll do is, we already have this x1 is bigger than c by square root of d minus 1. This thing we already have here. So what I'll do is, what we can observe is this square root of d minus 1 into x1 upon c is always greater than or equal to 1. This is the things we can note. And here we have 1. So this one I can write down that is less than or equal to this quantity. Therefore, what we can got is volume of A is less than or equal to square root C upon square root of D minus 1 to infinitive. Instead of 1, we are writing that quantity, that is x1 square root of D minus 1 by C into e power minus D minus 1 by 2 x1 square dx1, and to v of D minus 1 is already there, that we have already here. Now this v of D minus 1 divided by C into square root of D minus 1 is independent of this x1. C by square root of D minus 1 to infinitive. x1 into e power minus D minus 1 by 2 x1 square dx1 is there. Now the derivative of this one, it is D minus 1. So I'll just put D minus 1 by 2 x1 square is equal to t. So D minus 1 by 2 into 2x dx1 is equal to dt. So that will get cancelled out. So that will gives me dx1 will be x1 into dx1 will be dt upon square root of dt upon d minus 1.
D minus 1.
Okay, and we'll substitute that value here. And if you want, you can change this one also. Limits. That means if x1 is equal to c by square root of d minus 1, then t will be substitute here. We have d minus 1 by 2 x1 square is equal to t. So if I substitute this value here, that is d minus 1 by 2 c square upon d minus 1. D minus 1 will get cancelled out. So this will gives me c square by 2. And if x1 is infinitive, then t is also infinite. So the volume of A finally is less than or equal to integration from c square by 2 to infinitive. Sorry, this whole term is already there. Volume d minus 1 by c into square root of d minus 1, and that integration is there. Integration from c square by 2 to infinitive e power, because x1 into dx1 is this dt upon square root of d. This is e power minus t dt upon square root of, sorry, not square root of, only d minus 1. And if you take the integration, so this will gives me vd minus 1 by c upon 1 upon square root of d minus 1, that is the quantity left. If you take the integration of this quantity, that is e power minus t c square by 2 to infinity. If I put infinity here, then that quantity will become 0. And if I put c square by 2 here, something negative sign have taking a problem. Is there any mistakes we have did with the negative sign? Is minus t square. So it is 0 minus e power c square by 2, but this is a volume, so we not consider the negative sign. So what to do? Something mistake we have did here. It has to be positive sign. Here it is coming, if I put infinitive here, this will be 0 minus e power c square by 2. So ultimately, if I consider the positive sign, then the answer will be vd minus 1 by c into square root of d minus 1 into e power minus c square by 2. This is the upper bound, or I can say volume of A is less than or equal to this. I consider the positive sign. But why it is positive sign? What is the mistake we have did? This is e raised to minus t. What is here only? Consider this d minus 1 by 2 x1 square is d. This is 2 dx1 dt is there. Yeah, no problem with that. x1 dx1 is this. Yeah, so that is the problem is here. We have x1 square, so the square of this one, no problem. C square by d minus 1 is equal to t. So this is square by 2. No, this one is infinitive. T is infinitive. No problem. Substituting the value. So it gives me 1 by d minus 1. Something is mistaken here. Okay, anyway, this has to be positive. Some mistake is of negative sign is there, but this is the quantity we got. So finally, what we got is the volume of A is less than or equal to V of d minus 1 by c into square root of d minus 1 into e power minus c square by 2. Now ultimately what we need to obtain is this. Volume of A is, we got the upper bound of volume of A. Now we need to find out what will be the lower bound of the volume of H. Okay. So the H is the hemisphere that we have. So the hemisphere, what we can note, the volume of the hemisphere below the plane x1 is equal to 1 upon square root of d minus 1. So here this is the hemisphere, and there is one line, that is x is equal to 1 upon square root of d minus 1. So below this, that means this we are talking, is the lower bound of on the entire volume of the upper hemisphere. And this volume is at least that of cylinder. So what is this cylinder? This is the cylinder. You can just see that. Let me draw that cylinder. So here, this is the things. This is the portion I'm drawing. This portion from here to there. So it is kind of a cylinder we have. So that is the things we have. Now what is the height of this cylinder? And what will be the radius of this cylinder? That will gives me the volume of that cylinder. The height, that means from here to there, how much distance will be there. So that is this distance we are talking about. And what will be the radius will be there. So a cylinder of height, what should be the height? The height will be this much, 1 upon square root of d minus 1, because this distance is that 1 upon square root of d minus 1 is the height. And the radius is, the radius is this much, that is, so total radius is 1 we have. And if you subtract this much from that, so it is 1 minus square root of that. So it is square root of 1 minus 1 upon d minus 1. This will be the radius. So the volume of that cylinder is, first of all, it is a V d minus 1 is already there, because we are talking in d dimension, we are reducing the one dimension there, into radius. So the volume of a cylinder is radius, that is 1 upon d minus 1 raised to 1 by 2. So it is actually the, if you can talk in the two-dimensional sphere, three-dimensional cylinder, then the volume is pi r square h. That is the volume. So the square is because of it is a three-dimensional space. So it is a d minus 1 thing is here. So here you will have power d minus 1, into h, the height. The height is 1 upon square root of d minus 1. And that pi stands for this one. For example, you can just take that d equal to 3 here. Then this will be V2. V2 is nothing but the volume of, that is a pi, volume of a sphere in 2 dimensions. But sphere in 2 dimension is a circle with radius 1. So it is this pi stands for that. This is the radius r square. So it is 3, that is a square. So you can have this. And h is the height. So it is satisfying this in our 3-dimensional space. So this is the volume of the cylinder we have. Now there is another inequality we need to use here. So that inequality is this one. Using the fact, I will prove that one later on after completing this. Using this fact, that is 1 minus x raised to a is greater than or equal to 1 minus ax for all a is greater than or equal to 1. This is true. If we can use this fact here, that means what we can say is a volume of h is greater than or equal to, because we are finding the lower bound of that. The lower bound we have calculated like this, that is v d minus 1. And here I want to use this one. So it is 1 minus 1 upon d. Here instead of x we have 1 upon d minus a, and instead of a we have this quantity, that is d by d minus 1 upon 2. So what we are saying is here x is equal to 1 upon d minus 1 that we have here, and the value of a we can consider it is d minus 1 by 2. And if we use that one here, then you will see that it is 1 minus ax. Let me write first this thing, whole thing, that is 1 minus 1 upon d minus 1 power d by 2 into the height, that is 1 upon square root of d minus 1. Now we will use this fact, will gives you greater than or equal to, again because this quantity is greater than or equal to 1 minus ax. So v of d minus 1, as we use this one, we will have 1 minus a is d minus 1 by 2 into x is 1 upon d minus 1 into 1 upon square root of d minus 1. So finally, if you simplify this, this will give me 1 of d minus 1 upon v d minus 1 upon 2 into, because this will left with 1 by 2. 1 minus 1 by 2 will gives me 1 by 2 and into square root of d minus 1. So the volume of h is greater than or equal to this quantity. Ultimately, we need to find out the ratio, that is volume of a upon volume of h. That I can write down less than or equal to upper bound of volume of a upon lower bound of volume of h. But the upper bound of volume of a we have obtained it like this, that is this one, that is v of d minus 1 upon c into square root of d minus 1 e power c square. So we'll have v d minus 1 upon c into square root of d minus 1 e power minus c square by 2. And the lower bound of h we have calculated, that is this v d minus 1 upon 2 into square root of d minus 1. So just see that this v d minus 1 is cancelled out, d minus square root of d minus 1 is cancelled out. So what is left with is 2 by c e power minus c square by 2. And that completes the proof of this theorem. that is the most of the volume is 1 minus, so a whole is 1 minus this much, that is 2 by c e power c square by 2. That fraction we have proved that. One might ask why the computation of the lower bound on the total hemisphere, since it is one of the half unit ball, which is already known, because the total volume of the unit ball we already know, we already discussed in the previous lecture. That is, the volume of the unit ball is 2 by d pi raised to d minus 2 upon d into gamma d by 2. So this was the volume of the sphere we have. So hemisphere will have is half of this, that is 1 by 2 of this one. 2 will get cancelled. Why we have not used this much? The reason is we required the expression in terms of, here it is Vd minus 1 is used. Okay, so that's why this hemisphere is also have the in terms of Vd minus 1. So that's why we have calculated in the different manner, in different way to do this. Okay, and that completes the proof of this theorem that we have. If you have any question, you can ask.